I am so pleased you have found your way to this quiet place. You are resting with Science Blanket, your own soft space for a calm soul. Have you ever gazed at a far-off, shimmering light in the sky and felt as though you were seeing a slow, ancient dance? This evening, we are wrapping ourselves in the story of the stars, specifically the long, slow rising of the galaxies. We often see the sky as a dark room, but it is really a sea of swirling mists, billions of suns forming in a soft balance between the vast silence and the glowing clouds. From the light, swirling arms of stars that feel like silver silk to the deep, heavy centers that hold the memory of the beginning, a galaxy is the visible sign of the universe's invisible flow. As we begin, imagine yourself floating on a sea of warm starlight, feeling as loose and as easy as a cloud of dust in the sun. You do not need to know the laws of the heavens or the names of the distant worlds tonight. Just let the slow, swirling rhythm of the stars wash over you and tuck you in. Allow this blanket of light and space to be your guide as you move toward a deep and mindless rest. Now, take a slow, easy breath. Feel your chest rise and fall, as smooth and as sure as a low, humming wave. Let the heaviness of your day dissolve into the soft, blue shadows of the cosmos. Release your jaw, let your shoulders slide down, and sink into the softness of your bed. Let's explore the quiet wonders of the birth of galaxies together. In the vastness of space, tiny pockets of matter began to gather together long ago. Scientists use computer simulations and careful mathematical thinking to understand how these first collections of gas and dust behaved. They have found that certain proto-galaxies, which are like baby galaxies just starting to form, played a very special role in changing the universe. These proto-galaxies lived inside invisible cocoons called dark matter halos. The halos that mattered most had masses between 10 million and 100 million times the mass of our Sun. That might sound enormous, but compared to the galaxies we see today, these were actually quite small and delicate. What made them so important was that light could escape from them very easily. The gas in these systems was not held too tightly, so when stars began to shine, their light could flow outward into the surrounding emptiness without getting trapped inside. As time moved forward, more and more stars began to form within these early proto-galaxies. Each new star added its glow to the growing brightness. When you put many stars together, their combined light becomes incredibly powerful. This combined starlight began to have an effect on the hydrogen gas that filled all of space between the galaxies. Hydrogen is the simplest and most common element in the universe, and back then it existed as neutral atoms floating in the darkness. The energetic light from all those young stars started to strip electrons away from the hydrogen atoms, changing them into ionized hydrogen. This process is called ionization, and when it happened across the entire universe, we call it cosmic reionization. It did not happen all at once. Instead, it was a gradual process that unfolded over roughly the first billion years of cosmic history. Slowly but surely, the universe transformed from a dark place filled with neutral hydrogen into a more transparent space filled with ionized gas. This change ended what scientists call the Dark Ages, a time when the universe had cooled down after the Big Bang but had not yet made enough stars to light everything up again. While this was happening, something else was going on too. The early proto-galaxies were not just sitting still and making stars. They were moving through space, pulled by gravity toward one another. When two of these small systems came close enough, they would merge together, combining their stars, gas, and dark matter into a single larger object. This process is called hierarchical merging because it builds things from the bottom up, starting with small pieces and gradually creating bigger structures. Many early proto-galaxies experienced this kind of merging. Over time, the stellar content, which means all the stars and the dark matter of numerous small systems, were assimilated into larger and more recognizable galaxies. Imagine dozens or even hundreds of tiny puzzle pieces coming together to form a bigger picture. That is what happened as galaxies grew through mergers. When astronomers look out into space with their powerful telescopes, they are also looking back in time. This happens because light takes time to travel, so the farther away something is, the older the light we see from it. Through careful observations, scientists have discovered that recognizable galaxies, ones that look like actual galaxies rather than just fuzzy patches, already existed surprisingly early. These galaxies appeared between about 180 million years and 700 million years after the Big Bang. This period marks the main birth window for the first galaxies. It is amazing to think that within such a relatively short time after the universe began, structures we would call galaxies had already assembled themselves. The universe wasted no time getting organized. Some of the earliest galaxies astronomers have studied are truly ancient. The earliest galaxies with well-confirmed distances now reach what scientists call redshifts of around 14. Redshift is a way of measuring how much the universe has expanded since the light left a distant object. A redshift of 14 is extremely high, and it corresponds to only about 290 million years after the Big Bang. To put that in perspective, the universe is about 13.8 billion years old today, so these galaxies formed when the universe was only about 2% of its current age. Finding galaxies this early helps scientists understand just how quickly matter could clump together and start making stars. Before the year 2022, one of the record-holding early galaxies was called GNZ11. This galaxy dated to roughly 380 to 400 million years after the Big Bang. The discovery of GNZ11 showed that galaxies could assemble surprisingly quickly. It was a bit of a shock to find something so well developed so early in cosmic history. Scientists had models and predictions, but seeing actual galaxies like GNZ11 pushed those models and helped refine our understanding. It reminded everyone that the universe was efficient at turning gas clouds into shining collections of stars. When astronomers point their telescopes at very distant parts of the universe and collect light for many hours or even days, they reveal incredibly deep views of space. These deep observations show many very small and faint galaxies at high redshift. Some of these galaxies are so faint that they would be completely invisible without the most sensitive instruments. The discovery of so many small galaxies at great distances supports an important idea about how large galaxies grew. The idea is that big galaxies like our Milky Way were built from mergers of many smaller building blocks. Instead of forming all at once as one big object, galaxies grew by collecting smaller pieces over time. Each little galaxy contributed its stars and gas to the final product. This bottom-up construction process seems to be the way the universe preferred to build galaxies. As billions of years passed, the universe continued to evolve and galaxies took on different shapes and personalities. Today we see two main types of large galaxies: spiral galaxies and elliptical galaxies. Spiral galaxies have beautiful pinwheel shapes with arms that wind outward from the center. Elliptical galaxies look more like smooth footballs or spheres without much structure. These different shapes emerged from different assembly histories. When galaxies formed quietly over time without too many violent collisions, they could maintain ordered rotating disks of stars and gas, which became spirals. However, when galaxies experienced major mergers, the collisions would shake things up dramatically. Mergers tend to destroy those ordered disks because the gravitational forces scramble the neat orbits of stars. After a big merger, the stars end up moving in random directions rather than all rotating together. This builds up more spheroidal, elliptical systems. So the history of collisions and mergers a galaxy experienced determined what shape it would have billions of years later. Our own galaxy, the Milky Way, has its own special history written in its stars. The Milky Way has what astronomers call a thick disk, which is a puffy layer of older stars above and below the thin disk where the Sun lives. Scientists have studied the ages of stars in the thick disk and found that it likely began forming stars about 13 billion years ago. Since the universe is about 13.8 billion years old, that means the Milky Way's thick disk started forming only about 800 million years after the universe's birth. This makes our own galaxy a relatively early product of this long process of galaxy formation. When we look up at the night sky and see the band of the Milky Way stretching across the darkness, we are seeing a structure that began assembling itself when the universe was still very young. The story of galaxy formation did not end once individual galaxies had formed. Gravity continued to pull galaxies toward one another, just as it had pulled together the first proto-galaxies billions of years earlier. Galaxies began to fall together into groups and clusters. A group might contain a few dozen galaxies, while a cluster could have hundreds or even thousands of galaxies all bound together by gravity. These clusters themselves were organized into even larger structures called superclusters, which are vast networks of galaxy clusters spread across hundreds of millions of light-years. All of these structures formed as galaxies continued to fall together under gravity, building ever larger cosmic structures from the original tiny density ripples that existed shortly after the Big Bang. Those ripples were incredibly small differences in density from one place to another in the early universe, but over billions of years, gravity amplified them into the rich cosmic web of galaxies, clusters, and superclusters we see today. The universe started nearly smooth and featureless, but through the patient work of gravity acting over immense spans of time, it created the beautiful and complex tapestry of structure we observe all around us in the night sky. The birth of galaxies was not a single moment frozen in time, but rather the beginning of a story that continues even now. When we think about galaxies being born, we might imagine a clear starting point and ending point, like the birth of a baby. But galaxies are different. Even today, billions of years after those first galaxies appeared, galaxies are still evolving and changing. They continue to form new stars from clouds of gas. They pull in fresh gas from the space around them through a process called accretion, adding new material that can fuel more star formation. Galaxies also continue to merge with one another, just as they did in the early universe. When you look at it this way, the birth phase of galaxies blends smoothly into a continuous history of evolution rather than ending sharply. There is no moment where we can say a galaxy stopped being born and started just existing. Instead, galaxies grow and change throughout their entire lives, making the process of galaxy formation something that stretches across cosmic time. One of the most powerful tools we have for studying early galaxies is the James Webb Space Telescope, often called JWST for short. This incredible telescope was launched into space to see farther and more clearly than ever before. JWST has the ability to detect very faint and distant light, allowing it to peer back to times when the universe was extremely young. Recently, JWST has imaged galaxies at a redshift of 25. Remember that redshift tells us how much the universe has expanded since the light left an object. A redshift of 25 is extraordinarily high. It means the light from these galaxies was emitted just 100 million years after the Big Bang. Think about that for a moment. 100 million years sounds like a long time to us, but in the life of the universe it is barely a blink. The fact that galaxies already existed at this early time implies that galaxy formation started even earlier than many models had predicted. Scientists are now working to understand how galaxies could assemble so quickly, pulling together gas and dark matter and igniting their first stars in such a short period. What JWST has found is not just that early galaxies existed, but that some of them were surprisingly mature and organized. When astronomers first began thinking about the earliest galaxies, many imagined they would be chaotic and unstructured. After all, these were the first attempts by the universe to build galaxies, so it seemed reasonable to expect messy, irregular blobs of stars rather than elegant structures. However, some early galaxies discovered by JWST show mature spiral arms and organized star clusters. These features are the kinds of things we see in well-developed galaxies much later in cosmic history. Finding them so early challenges old ideas about what primordial galaxies should look like. It suggests that galaxies could become organized and structured much more quickly than scientists had thought possible. The universe, it seems, knew how to make beautiful spirals right from the start. One particularly striking example is a galaxy called Alexander. This is a grand-designed spiral galaxy, which means it has prominent, well-defined spiral arms much like those we see in our own Milky Way. What makes Alexander so remarkable is its age. JWST discovered that this Milky Way-like galaxy formed only 1.5 billion years after the Big Bang. At that time, the universe was merely a tenth of its current age. It is astonishing to find such a mature, organized structure so early. Alexander shows that the processes that create spiral galaxies were already working efficiently when the universe was still in its childhood. The stars in Alexander's spiral arms are arranged in graceful curves, guided by gravity and rotation just like the arms of galaxies we see nearby today. JWST has also revealed that early galaxies seen between 500 and 700 million years after the Big Bang had masses comparable to the modern Milky Way. In other words, these galaxies contained as many stars and as much gas as our own galaxy does today, but they managed to assemble all that material in a fraction of the time. This discovery has sparked debates among scientists about how rapid early star formation could have been. To build a galaxy as massive as the Milky Way in just 500 million years requires incredibly efficient star formation. Gas must have collapsed into stars very quickly, and those stars must have been forming at high rates continuously. Understanding exactly how this happened is one of the big questions driving current research in galaxy formation. Over the years, scientists have developed different models to explain how disk galaxies, like spirals, could form. One approach is called the top-down model. In this picture, disk galaxies formed through what is known as monolithic collapse. Imagine a very large cloud of gas sitting in space. If this cloud collapses under its own gravity all at once, it could form a galaxy directly. But there is a problem. How does the disk get its spin? After all, spiral galaxies are rotating, with stars and gas moving in organized circular orbits. The top-down model explains this through something called tidal torques. As the gas cloud collapses, it feels gravitational tugs from nearby clumps of dark matter. These tugs are not perfectly symmetrical, so they twist the collapsing cloud, imparting angular momentum to it. Angular momentum is just a fancy way of saying spin. This spin causes the gas to settle into a rotating disk rather than falling straight to the center. The top-down model was popular for a while because it seemed like a straightforward way to make disk galaxies. However, there is another model that fits the observations even better. This is called the bottom-up hierarchical model. Instead of starting with one big collapse, this model starts with small dark matter clumps merging into larger halos over time. Remember that dark matter is invisible material that makes up most of the mass in the universe. It clumps together first, creating gravitational wells that attract normal matter. In the hierarchical model, many small dark matter clumps form early on, and they gradually merge together to build bigger structures. This approach better matches the observed abundance of small galaxies over large ones. When we look at the universe, we see many more small, faint galaxies than giant ones. The hierarchical model naturally produces this distribution because it builds from the bottom up. Small galaxies form first and are abundant, while larger galaxies take longer to assemble through mergers. Most astronomers today favor the hierarchical model because it agrees so well with what we actually see. Inside the halos where galaxies are forming, the gas is not sitting still and calm. Instead, it is churning and swirling with what scientists call supersonic turbulence. Supersonic means faster than the speed of sound, and turbulence refers to chaotic, swirling motions like what you see in a rushing river. This turbulence in protogalactic halos can be driven by several things. Supernova explosions, which happen when massive stars die, blast energy and gas outward, stirring up the surrounding material. Mergers between halos also create turbulence as gas clouds smash together. This turbulence is actually helpful for star formation in an interesting way. Instead of allowing all the gas to collapse into a single massive star, the turbulence helps fragment the gas into multiple star-forming clouds. Each cloud can then collapse separately, forming many stars instead of just one. This is why galaxies contain millions or billions of stars rather than one enormous star at the center. While turbulence stirs things up, there is also a steady flow of fresh material coming into young galaxies. Cold gas accretion streams feed the centers of the first galaxies, bringing in new fuel for star formation. These streams are like rivers of gas flowing along the cosmic web, channeling material from the surrounding universe into the galaxy. As this cold gas falls inward, it generates turbulence that actually helps support rotationally supported disks even before significant star formation has occurred. In other words, the process of gas falling in creates the conditions for a rotating disk to form. The infalling gas carries angular momentum with it, and the turbulence helps spread that spin throughout the disk. By the time stars begin forming in large numbers, the disk is already spinning and organized. The first massive stars that formed in these early galaxies had a powerful effect on their surroundings. These stars were extremely bright and hot, pouring out intense radiation. When they died, they exploded as supernovae, releasing tremendous amounts of energy. Together, the radiation and supernovae from the first massive stars provided what scientists call stellar feedback. Feedback means the stars were affecting their environment, changing the conditions around them. This stellar feedback delayed subsequent star formation in the host halos. The energy from the stars would heat up the remaining gas, making it harder for that gas to collapse and form new stars. The delay lasted for times comparable to the halo's dynamical timescale, which is roughly the time it takes for material to orbit through the halo or for the halo to respond to changes. This feedback created a natural regulation system. A burst of star formation would produce massive stars. Those stars would inject energy, and that energy would slow down the next round of star formation. This prevented galaxies from using up all their gas at once and helped spread star formation out over time. During the period known as cosmic dawn, when the very first galaxies were taking shape, galaxy formation did not proceed smoothly and steadily. Instead, it happened in short bursts that lasted between 5 and 30 million years. These bursts were punctuated by intense stellar feedback that temporarily halted further collapse. Imagine a cycle that repeated over and over. Gas would collapse inward under gravity, forming a flurry of new stars in a relatively brief period. Then those stars, especially the most massive ones, would unleash their energy through radiation and eventually supernova explosions. This flood of energy would heat up the remaining gas and push it around, stopping the collapse. For a while, no new stars could form because the gas was too hot and energetic. But eventually, the gas would cool down again, gravity would start pulling it back together, and another burst of star formation would begin. This start and stop rhythm characterized the early growth of galaxies, giving them a fitful, pulsing quality as they gradually built up their stellar populations. One of the great mysteries that scientists are working to solve involves supermassive black holes and their relationship with galaxies. Supermassive black holes are objects millions or even billions of times more massive than our Sun, and they sit at the centers of most large galaxies today. The puzzle is about timing and causation. Did supermassive black holes form early in the universe, with galaxies potentially growing around them afterward? Or did galaxies form first, creating the conditions that allowed black holes to grow at their centers? This is a classic chicken or egg question, and astronomers are not yet sure of the answer. Some observations suggest that supermassive black holes existed very early, perhaps even before their host galaxies were fully formed. If that is true, the black holes might have influenced how the galaxy grew around them. On the other hand, maybe galaxies formed first and then funneled gas into their centers, feeding the growth of central black holes. The James Webb Space Telescope is specifically designed to help resolve this puzzle by observing the earliest black holes and galaxies and figuring out which came first or whether they grew together hand in hand. Once black holes exist at the centers of galaxies, they can have a powerful influence on their surroundings. When matter falls toward a black hole, it does not just disappear quietly. Instead, it forms a swirling disk around the black hole and heats up to tremendous temperatures, shining brightly and sometimes shooting out jets of energy. When a black hole is actively feeding and shining like this, we call the galaxy's center an active galactic nucleus. The energy released by active galactic nuclei provides feedback to the galaxy, and this feedback operates in different modes. One mode is called quasar mode, which happens when the black hole is feeding vigorously and producing intense radiation and powerful winds that blast outward. The other is radio mode, which is gentler and involves jets of particles streaming out at nearly the speed of light. Both modes help regulate black hole growth and star formation in the galaxy. The energy from the black hole can heat or push away gas that would otherwise fall into the center to feed either the black hole or new star formation. In this way, black holes act as thermostats, preventing galaxies from growing too large or forming stars too quickly. Not all galaxies are giant spirals or massive ellipticals. Many galaxies in the universe are dwarf galaxies, which are much smaller and contain far fewer stars. Though small, dwarf galaxies outnumbered larger ones in the early universe and played an outsized role in an important cosmic event. These little galaxies dominated cosmic reionization by producing ionizing photons from their first stars. Even though each dwarf galaxy might not produce as much light as a larger galaxy, there were so many of them that their combined output was enormous. The stars in dwarf galaxies, especially the hot, massive stars, emitted high-energy ultraviolet light that could ionize hydrogen atoms. Because dwarf galaxies were so numerous, they collectively provided most of the photons needed to reionize the universe. However, dwarf galaxies had a vulnerability. They are sensitive to feedback because they have weaker gravity than larger galaxies. When stars exploded as supernovae, the energy could blow gas completely out of a dwarf galaxy, stopping star formation. Despite this sensitivity, dwarf galaxies still manage to be the heroes of reionization. When we think about what provided the light that reionized the universe, we might imagine that quasars and other galactic nuclei with growing black holes played a major role. After all, quasars are incredibly bright and can be seen across vast distances. However, observations and calculations show that quasars and galactic nuclei contributed negligibly to reionization photons. They simply were not numerous enough in the early universe to provide the bulk of ionizing light. Instead, ordinary star-forming galaxies provided the photons needed to reionize the universe. These galaxies were not exotic or unusual. They were just regular galaxies filled with young, hot stars churning out ultraviolet light. The lesson here is that sometimes the most common and ordinary objects, when they exist in large numbers, can have a bigger impact than rare, spectacular ones. As galaxies age and evolve over billions of years, many of them undergo a transformation known as galaxy quenching. This process shifts blue star-forming spiral galaxies into red passive elliptical galaxies. Blue galaxies are called blue because they contain many young, hot stars that emit blue light. These galaxies are actively forming new stars and are full of gas and dust. Red galaxies, on the other hand, appear red because they contain mostly older, cooler stars and have little or no ongoing star formation. The transition from blue to red happens rapidly, not over many billions of years but sometimes in just a few 100 million years. Galaxy quenching occurs through gas removal or prevention of new cold gas inflow. If a galaxy loses its gas, either because it gets stripped away or because something prevents new gas from flowing in, it can no longer form new stars. Without fresh fuel, star formation grinds to a halt, and the galaxy slowly reddens as its blue stars age and die without being replaced. Different mechanisms can quench galaxies depending on their environment and mass. One process, charmingly called strangulation, quenches low-mass galaxies by cutting off their cold gas supply. This often happens when a smaller galaxy falls into a large cluster of galaxies. The cluster is filled with hot gas, and as the smaller galaxy moves through this environment, its own cold gas can be stripped away or heated up. Without cold gas, the galaxy can no longer form stars, and it gradually fades. Another quenching mechanism affects galaxies sitting in massive dark matter halos. When gas falls into a very massive halo, it can be heated to extremely high temperatures by what is called virial shock heating. This heating happens because the gas crashes into the halo at high speed, converting its motion into heat. Once heated, the gas is too hot to cool down and collapse into stars, effectively shutting off star formation. Both strangulation and virial shock heating are ways that a galaxy's environment can end its star-forming life. To understand all these complex processes in detail, scientists create computer simulations that model how galaxies form and evolve. These are called hydrodynamic simulations because they track the flow and behavior of gas, which is a fluid. The simulations must include what scientists call baryonic physics. Baryons are just the normal particles that make up atoms, like protons and neutrons, so baryonic physics refers to all the processes that affect normal matter as opposed to dark matter. This includes how gas cools when it radiates energy away, especially through the presence of metals, which in astronomy means any element heavier than hydrogen and helium. It includes turbulence, the chaotic swirling motions in gas. And it includes feedback from stars and black holes. The simulations also need to reproduce the multiphase interstellar medium, which means the fact that gas in galaxies exists at many different temperatures and densities all at once. Some gas is cold and dense, forming stars. Some is warm and spread out. Some is hot and thin. Getting all these phases to coexist realistically in a simulation is a major challenge, but it is necessary to create virtual galaxies that look and behave like real ones. One important parameter that simulations must get right is the star formation efficiency. This tells us how quickly gas turns into stars. In the simulations, star formation efficiency in molecular gas, which is the cold, dense gas where stars actually form, is about 1% per freefall time. Freefall time is the amount of time it would take for a cloud of gas to collapse under its own gravity if nothing else interfered. So this means that in each freefall time, only about 1% of the available molecular gas actually turns into stars. The rest remains as gas or gets disrupted by turbulence and feedback. This low efficiency might seem surprising, but it matches what we observe in real galaxies. Star formation is not a runaway process. Instead, it proceeds slowly and is regulated by many factors that prevent all the gas from turning into stars at once. Some of the most sophisticated simulations of galaxy formation are the illustrious TNG simulations. These are enormous computational projects that follow the formation and evolution of thousands of galaxies from the early universe to the present day. The illustrious TNG simulations show galaxies forming with detailed structures that closely resemble real galaxies. They produce spiral galaxies with graceful arms, elliptical galaxies with smooth profiles, and everything in between. One particularly impressive feature is that the simulations can form bars in spiral galaxies. A bar is a straight or slightly curved structure of stars that stretches across the center of some spiral galaxies, including our own Milky Way. Bars form from stellar density waves, which are ripples in the distribution of stars that propagate through the galaxy's disk. These density waves are not made of the same stars all the time. Instead, stars move in and out of the wave, much like cars moving through a traffic jam. The density wave itself, however, maintains its shape and can create a bar structure. The fact that illustrious TNG simulations naturally produce bars without being specifically programmed to do so is a sign that the simulations are capturing the real physics of galaxy formation. It gives scientists confidence that these virtual galaxies can teach us about how real galaxies came to be. One of the most intriguing discoveries in modern astronomy is a relationship between two things that seem completely different: supermassive black holes at the centers of galaxies and the motion of stars far away from those black holes. This relationship is called the M-sigma relation, and it links the mass of a supermassive black hole to something called the velocity dispersion of stars in elliptical galaxies. Velocity dispersion is a measure of how fast stars are moving in random directions within the galaxy. If stars are zipping around quickly in all directions, the velocity dispersion is high. If they are moving more slowly, it is low. What astronomers discovered is that the more massive the central black hole, the higher the velocity dispersion of stars throughout the galaxy. This correlation is remarkably tight, meaning it holds true for galaxy after galaxy. The M-sigma relation tells us something profound. Black holes and their host galaxies are deeply connected. Even though the black hole is tiny compared to the entire galaxy, its growth must somehow be tied to the galaxy's overall formation and evolution. This connection supports the idea that black holes and galaxies grow together, influencing each other through feedback and gravitational effects. Among the most distant objects ever observed is a galaxy with the catalog name GHz 2, also known as Glass Z12. This remarkable object holds the distance record at a redshift of 12.34. At that redshift, we are seeing the galaxy as it was just 330 million years after the Big Bang. What makes GHz 2 especially valuable is that astronomers obtain spectra from it. A spectrum breaks down light into its component colors and reveals detailed information about the galaxy's composition, temperature, motion, and more. The spectra from GHz 2 provide unprecedented details about what galaxies were like at this incredibly early time. Scientists can study the elements present in the galaxy, the ages of its stars, and how fast it is moving. Each spectrum is like a fingerprint that tells the story of that particular galaxy. Finding such a distant galaxy and being able to study it in such detail is a triumph of modern observational astronomy. Other early galaxies have also captured attention because of their unexpected brightness. Two examples are Mais's galaxy and CERS 1019, which formed between 390 and 410 million years after the Big Bang. When astronomers first detected these galaxies, they were surprised by how luminous they appeared. For galaxies so young, they were shining much more brightly than expected. This brightness suggests they were forming stars at a very high rate, or perhaps that they already contained more stars than models predicted they should have at that age. Luminous early galaxies like Mais's galaxy and CERS 1019 challenge our understanding of how quickly galaxies could build up stellar mass. They push scientists to reconsider the efficiency of star formation in the early universe and to think about whether there might be processes we have not fully accounted for yet. Sometimes nature provides astronomers with a helpful magnifying glass in the form of gravitational lensing. Gravitational lensing happens when a massive object, like a galaxy cluster, sits between us and a more distant object. The gravity of the massive object bends the light from the distant object, magnifying it and making it appear brighter and larger than it would otherwise. This effect was crucial for studying Alexander, the early spiral galaxy mentioned earlier. A massive galaxy cluster called Abell 2744 acted as a gravitational lens, magnifying Alexander and allowing the James Webb Space Telescope to resolve its spiral arms in detail. Without this natural magnification, Alexander would have been too faint and too small to study so thoroughly. Gravitational lensing effectively gives astronomers a more powerful telescope for free, courtesy of the universe's own geometry. Abell 2744 is sometimes called Pandora's cluster, and it has helped reveal many distant galaxies that would otherwise remain hidden. In the year 2025, astronomers discovered a truly unusual galaxy, a nine-ringed giant. Most galaxies do not have rings at all, and when they do, it is usually just one or two. A galaxy with 9 distinct rings is extraordinarily rare and offers important clues about ring formation. Rings in galaxies can form through different processes. One possibility is mergers, where the collision and interaction of two galaxies create ripples that settle into ring-like structures. Another possibility is instabilities within the galaxy itself, where waves or oscillations in the disk naturally organize into concentric rings. Studying this nine-ring giant helps astronomers understand which processes are most important for creating rings and under what conditions they occur. Each ring is like a historical record, preserving information about events that happened in the galaxy's past. The James Webb Space Telescope has not only found early galaxies but has also detected specific substances within them. One important discovery involves carbonaceous dust grains in galaxies at redshift around 7. Carbonaceous means the dust contains carbon, and these particular dust grains have a very specific signature. They produce what is called the 2175 angstrom extinction bump. An extinction bump is a feature in the spectrum where dust absorbs light at a particular wavelength, creating a bump or dip in the observed light. The 2175 angstrom bump is well known in our own galaxy and nearby galaxies, and it indicates the presence of carbon-rich dust. Finding it in galaxies at redshift 7, when the universe was much younger, tells us that carbon had already been produced and incorporated into dust grains. This means that enough stars had lived and died by that time to create carbon through nuclear fusion and spread it through space when they exploded. Another type of carbon-rich molecule that JWST has detected in early galaxies is polycyclic aromatic hydrocarbons, often abbreviated as PAHs. These are molecules made of carbon and hydrogen arranged in rings. PAHs are important in interstellar space and are thought to play a role in the chemistry that happens in gas clouds. JWST detected PAHs through a spectral feature at 3.3 micrometers in a galaxy at redshift around 4. The 3.3 micrometer feature is a characteristic signature of PAH molecules. Finding PAHs in such an early galaxy shows that complex carbon chemistry was already happening less than 2 billion years after the Big Bang. This is earlier than many scientists expected and suggests that the chemical enrichment of galaxies proceeded rapidly. Speaking of chemical enrichment, carbon enrichment in general reached significant levels remarkably early. Studies of early galaxies show that carbon had built up to substantial abundances by just 350 million years after the Big Bang. Carbon is made inside stars through nuclear fusion. When stars die, especially massive stars that explode as supernovae, they release the carbon they have created into space. That carbon then becomes part of the next generation of stars and can also form dust and molecules. The fact that carbon enrichment was already significant so early means that the first generations of stars must have formed, lived, and died very quickly. The universe wasted no time in cycling matter through stars and building up the elements we see today. Astronomers also study the physical conditions inside early galaxies by measuring properties like electron density. Electron density tells us how many free electrons exist in a given volume of gas. This is important because it affects how gas cools, how it emits light, and how it responds to radiation. JWST observations have allowed scientists to trace how electron densities in galaxies evolved from redshift 9 all the way down to redshift 0, which is the present day. This measurement is possible through careful analysis of spectral line profiles, which are the shapes of emission or absorption features in a spectrum. Different densities produce different line shapes, so by studying those shapes, astronomers can infer the density of the gas. Watching how electron densities changed over cosmic history gives insights into how the interstellar medium in galaxies evolved as the universe aged. One of the most surprising results from JWST has been the discovery of bright early galaxies that seem to have more stellar mass than expected. These galaxies exceed the predictions of the lambda-CDM model, which is the standard model of cosmology that includes dark energy, cold dark matter, and the observed expansion history of the universe. According to lambda-CDM, there should only be a certain amount of matter available in the early universe to form galaxies, and that matter should take time to collapse and turn into stars. But JWST has found galaxies at redshift greater than 10 that are brighter and more massive than the model predicts. This does not necessarily mean the lambda-CDM model is wrong, but it does mean that something about our understanding of how efficiently stars formed in the early universe might need adjustment. Perhaps star formation was more efficient than we thought, or perhaps there were other processes helping to build stellar mass quickly. These bright early galaxies are currently one of the hottest topics in galaxy formation research. The discoveries of bright and massive early galaxies have led some scientists to explore alternative explanations for what we observe. One idea that has gained renewed attention is modified Newtonian dynamics, often called MOND for short. This proposal suggests that gravity might work slightly differently than Newton and Einstein described, especially in regions where gravitational forces are very weak. Some researchers argue that modified Newtonian dynamics better fits the rapid early galaxy assembly we see in JWST data without requiring dark matter to be as dominant as it is in standard models. In the conventional view, dark matter provides most of the gravitational pull that allows galaxies to form, but in MOND, a modification to gravity itself could potentially explain why galaxies assemble so quickly. This is still a controversial idea, and most astronomers continue to favor the dark matter paradigm because it explains so many different observations across the universe. However, the tension between what JWST sees and what models predict has kept alternative theories like MOND in the conversation. Science progresses by considering multiple possibilities and testing them against observations. When we think about where the first true galaxies formed, we need to consider the environment they required. Atomic cooling halos with masses of around 100 million solar masses at redshift around 10 provided the right conditions to host the first bona fide galaxies. These halos are called atomic cooling halos because the gas in them can cool by radiating energy away through atomic processes, primarily the emission of light by hydrogen atoms. Cooling is essential for galaxy formation because hot gas resists collapse. Only when gas cools can it become dense enough to form stars. Halos smaller than about 100 million solar masses cannot cool efficiently through atomic processes, so they struggle to form stars. Halos much larger are rare at high redshift. So these atomic cooling halos of around 100 million solar masses hit a sweet spot where they were both common enough to be numerous and massive enough to cool and form stars. They represent the nurseries where the first recognizable galaxies came to life. Despite the sophistication of modern computer simulations, they still face challenges in reproducing everything we observe. One particular difficulty involves baryonic feedback, which is the energy returned to the gas by stars and black holes. Simulations include feedback in their calculations, but there are limitations to how accurately they can model all the complex physical processes involved. These baryonic feedback limitations in simulations make it difficult to match JWST's observations of compact galaxies. Some of the galaxies JWST has found are very small and dense, with their stars packed tightly together in a small volume. Getting simulations to produce such compact structures is hard because feedback tends to puff galaxies up by injecting energy and preventing gas from collapsing too tightly. If the feedback is too strong, galaxies become too diffuse. If it is too weak, galaxies might form too many stars too quickly. Finding the right balance to match the diverse range of galaxy structures we observe is an ongoing challenge for theorists. Among the many intriguing objects JWST has found are 3 galaxies that astronomers affectionately describe as fuzzy red smudges. These galaxies appeared in images taken by JWST and date to between 400 and 600 million years after the Big Bang. They are called fuzzy because they do not have sharp, well-defined edges or structures. They appear as soft, indistinct patches of light. They are red because their light has been redshifted by the expansion of the universe and because they may contain older stars or significant amounts of dust, both of which make galaxies appear redder. These fuzzy red smudges are mysterious. Scientists are working to understand exactly what they are. They might be very dusty galaxies, or they could be galaxies in an unusual phase of their evolution, or they might represent a population of objects we have not fully characterized yet. Their fuzzy appearance makes them difficult to study in detail, but they hint at the diversity of galaxy types that existed in the early universe. JWST has also observed supermassive black holes in the act of growing. One early galaxy contains a feasting supermassive black hole that shows clear signs of active growth. The black hole is pulling in gas from its surroundings and heating it up as it falls inward. This process releases enormous amounts of energy, making the center of the galaxy shine brightly. By studying this black hole, astronomers can learn how quickly black holes could grow in the early universe and how they interacted with their host galaxies. A feasting black hole is one that is actively accreting matter, meaning it is consuming gas at a high rate. This accretion makes the black hole gain mass rapidly. Observing such a system in a very early galaxy helps address the puzzle of how supermassive black holes could become so massive so quickly. If black holes are feasting efficiently from early times, they can reach enormous masses within the first billion years of cosmic history. When astronomers look at the shapes of early galaxies, they often see chaos rather than order. Early galaxies exhibit chaotic morphologies before settling into the more organized disks and elliptical shapes we see in mature galaxies. A chaotic morphology means the galaxy looks irregular and lumpy, without clear spiral arms or a smooth structure. This makes sense when we think about what is happening inside these young galaxies. They are forming stars rapidly, often in clumps scattered throughout the galaxy. They are experiencing mergers with other small galaxies, which disrupts their structure. Supernova explosions and stellar winds are blasting gas around, creating bubbles and distortions. All of these processes create a turbulent, messy appearance. Only after hundreds of millions of years, when star formation becomes more regulated and mergers become less frequent, do galaxies settle down into the elegant spirals and smooth ellipticals we know today. The chaotic phase is a natural part of growing up for a galaxy. While JWST has provided stunning new views of the early universe, it does not work in isolation. Data from the Hubble Space Telescope, which has been observing the universe for more than 3 decades, continues to play an important role. HST data helps constrain JWST anomalies by matching lower redshift counts. What this means is that Hubble has observed many galaxies at somewhat lower redshifts, closer to us than the most distant JWST targets. By comparing the number of galaxies Hubble sees at these intermediate distances with what JWST sees at higher redshifts, astronomers can check whether the trends make sense. If JWST finds an unexpectedly large number of bright galaxies at very high redshift, scientists can look at Hubble data to see if the numbers gradually increase as expected when moving to slightly lower redshifts. This cross-checking helps ensure that surprising JWST results are real and not due to some systematic error or misinterpretation. Hubble and JWST work together as complementary tools, each contributing to a more complete picture. To understand why galaxies exist at all, we need to go back to the very beginning of the universe. The tiny density variations that eventually grew into galaxies originated from quantum fluctuations. These quantum fluctuations arose from Heisenberg's uncertainty principle, a fundamental rule in quantum mechanics that says you cannot know both the position and momentum of a particle with perfect precision. In the incredibly early universe, during a period called inflation when the universe expanded exponentially fast, quantum fluctuations in the fabric of spacetime were stretched out to enormous sizes. These stretched fluctuations became the seeds of structure in the universe. Some regions ended up slightly denser than average, and some slightly less dense. Over billions of years, gravity amplified these tiny differences, turning them into the galaxies, clusters, and cosmic web we see today. It is remarkable to think that the largest structures in the universe, spanning hundreds of millions of light-years, originated from quantum effects at the smallest scales imaginable. In the very early universe, conditions were dramatically different from today. Before about 300,000 years after the Big Bang, radiation dominated over matter. This means that the energy density of light and other radiation was greater than the energy density of matter. Photons, the particles of light, were so energetic and numerous that they exerted more gravitational influence than atoms. The universe was also opaque during this time because photons could not travel far without scattering off free electrons. Matter and radiation were tightly coupled together in a hot, dense plasma. Only after the universe expanded and cooled enough for electrons to combine with protons to form neutral hydrogen atoms did radiation decouple from matter. This event, called recombination, happened around 300,000 years after the Big Bang. After recombination, radiation could stream freely through space, and matter became the dominant component controlling the gravitational dynamics of the universe. This transition from radiation domination to matter domination was a critical turning point that set the stage for structure formation. In the 1960s, three astronomers named Egan, Lyndon Bell, and Sandiage proposed an influential model for how our Milky Way galaxy formed. They suggested that the galaxy came together through monolithic collapse of large gas clouds. In their picture, a huge cloud of primordial gas collapsed rapidly under its own gravity, and as it collapsed, it formed stars. The stars that formed early, while the cloud was still roughly spherical, became the stars of the halo and thick disk. As the gas continued to collapse and settled into a rotating disk, later generations of stars formed in the thin disk where the Sun now resides. This monolithic collapse scenario was elegant and simple. It explained many features of the Milky Way, such as why older stars are found in the halo and why younger stars are in the disk. However, as observations improved and computer simulations became more sophisticated, it became clear that the Milky Way's history was more complicated than a single collapse. The galaxy likely formed through a combination of collapse and mergers, with smaller galaxies being absorbed over time. Still, the Egan-Linden-Bell-Sandage model was an important step in understanding galaxy formation and sparked decades of research into the processes that build galaxies. To help visualize how a rotating gas cloud collapses to form a galaxy, astronomers sometimes use what they call the pizza dough analogy. Imagine a ball of pizza dough spinning slowly. As you toss it and spin it faster, the dough flattens out into a disc shape, getting thinner in the middle and keeping most of its mass in a flat plane. This is very similar to what happens to a collapsing gas cloud. As the cloud collapses under its own gravity, conservation of angular momentum causes it to spin faster, just like a figure skater spins faster when pulling their arms in. The spinning forces the cloud to flatten into a disc shape rather than collapsing into a sphere. Material can fall inward toward the center relatively easily along the rotation axis, but it resists falling inward in the plane of rotation because of the centrifugal effect from the spin. The result is a flat, rotating disk where stars can form. This pizza dough analogy captures the essential physics of why disk galaxies are flat and why they spin. It is a simple way to understand a complex process that involves gravity, rotation, and the conservation of angular momentum working together. The very first galaxies were not quite like the galaxies we see today. They were simpler and less organized. These early structures are called proto-galaxies, and they were essentially gas clouds with embedded first stars. A protogalaxy might not have had a well-defined shape or a clear disk structure. Instead, it was a region where gas had collected and started forming stars. The first stars within these proto-galaxies were probably quite massive and hot, burning brightly but living short lives. As these stars lived and died, they enriched the gas around them with heavier elements. Over time, more stars formed, the gravitational pull strengthened, and the protogalaxy gradually took on the characteristics of a full-fledged galaxy. But in the beginning, the distinction between a protogalaxy and a galaxy was somewhat fuzzy. A protogalaxy was a galaxy in the process of becoming, a work in progress that would eventually mature into something more recognizable. When astronomers study how galaxies formed, they rely on observations that reveal the underlying processes at work. One key insight came from observed processes that showed denser dark matter regions attracted hydrogen gas clouds. Remember that dark matter makes up most of the mass in the universe, and it clumps together first because it does not interact with light or normal matter except through gravity. Where dark matter is dense, its gravitational pull is strong. Hydrogen gas, which is the most abundant element, responds to this gravitational pull and flows toward the dark matter concentrations. As gas accumulates in these regions, it becomes dense enough to cool and eventually form stars. This observation confirmed the theoretical expectation that dark matter acts as the scaffolding for galaxy formation. The dark matter provides the gravitational wells, and normal matter falls into those wells and lights up as stars. Without dark matter, the gas would not have collected efficiently enough to form galaxies as quickly as we observe. As scientists studied galaxies more carefully, they realized that the simple monolithic collapse picture might not be the whole story. In 1978, two astronomers named Searle and Zinn introduced a different idea. They proposed what is sometimes called top-down coalescence of small progenitors, though this is a bit of a confusing name because it is actually more of a bottom-up process. What Searle and Zinn suggested was that galaxies formed through the coming together of many smaller building blocks rather than from a single large collapse. They looked at the distribution of old star clusters in the Milky Way's halo and noticed that these clusters had a range of chemical compositions, suggesting they formed in different places at different times. This supported the idea that the halo was built up from many smaller proto-galaxies that merged together. The Searle-Zinn scenario was an early version of what we now call hierarchical assembly, and it challenged the prevailing monolithic collapse model. It encouraged astronomers to think about galaxy formation as a process involving many mergers over time. The hierarchical assembly process involves proto-galaxies colliding and merging under the influence of gravity. Picture many small gas clouds, each containing some dark matter and some stars, scattered through a region of space. Gravity pulls them toward one another. When two proto-galaxies get close enough, they begin to orbit each other, and eventually they collide and merge. Each merger adds mass to the growing galaxy. Over time, through countless collisions and mergers, small proto-galaxies build up into the large galaxies we see today. This hierarchical assembly process explains why we see so many small galaxies in the early universe and why larger galaxies become more common over time. It is a bottom-up construction where small pieces gradually assemble into bigger structures. The process continues even today, though at a slower pace, as galaxies in dense regions occasionally merge with one another. One of the most remarkable structures discovered in recent years is called SPT 2349-56. This is a baby galaxy cluster, a region where many galaxies are in the process of forming close together. What makes SPT 2349-56 especially interesting is that it contains intracluster gas that is hotter than predicted by models. Intracluster gas is the gas between galaxies in a cluster, and it can be heated by various processes such as shock waves from galaxy motions and energy injected by supermassive black holes. In SPT 2349-56, the gas appears to be even hotter than expected for such an early cluster. This suggests that energetic processes were at work very early in the cluster's history. The excess heat might come from intense star formation, from active galactic nuclei, or from the violent collisions of galaxies within the cluster. Understanding why the gas is so hot helps astronomers learn about the physical conditions in the densest regions of the early universe where galaxy clusters were being born. The Hubble Space Telescope captured one of the most famous images in astronomy called the Hubble Ultra Deep Field. This image was created by pointing Hubble at a tiny, seemingly empty patch of sky and collecting light for many hours. The result was a picture filled with thousands of galaxies at various distances and ages. One of the key insights from the Hubble Ultra Deep Field is that it clearly shows small galaxies merging into larger ones. You can see galaxies that appear to be interacting, with distorted shapes and tidal tails of stars pulled out by gravitational forces. You can see pairs of galaxies close together, in the process of colliding. By studying these mergers across cosmic time, astronomers confirmed that hierarchical assembly through mergers is the dominant way galaxies grow. The ultra-deep field provided direct visual evidence that galaxies are not isolated islands but dynamic systems that frequently interact and combine with their neighbors. As observational techniques improve, astronomers can see finer and finer details in distant galaxies. At redshift 6, which corresponds to when the universe was less than 1 billion years old, observations now have the resolution to see star-forming clumps down to scales of 20 to 80 parsecs. A parsec is about 3¼ light-years, so 80 parsecs is around 260 light-years. At this scale, astronomers are seeing individual regions where stars are forming within early galaxies, not just the galaxy as a whole. These clumps are like the stellar nurseries in our own galaxy, but observed at cosmic dawn. Being able to resolve such small structures allows scientists to study how star formation was distributed within early galaxies. They can see whether star formation happened uniformly throughout the galaxy or in concentrated bursts within specific clumps. This level of detail is crucial for understanding the physical processes driving star formation in the early universe. When studying how galaxies evolve, astronomers have noticed that galaxies do not all follow the same path. This observation is captured in something called galaxy assembly bias, which shows that quiescent galaxies, meaning galaxies that are no longer forming stars, evolved via two distinct paths. Some galaxies became quiescent because they ran out of gas through internal processes like strong stellar feedback that expelled their gas. Others became quiescent because of environmental effects, such as falling into a galaxy cluster where their gas was stripped away. The fact that there are two paths to becoming quiescent shows that both internal properties and external environment play important roles in galaxy evolution. Assembly bias means that galaxies with the same mass can have different properties depending on how they formed and where they live. This complexity makes understanding galaxy evolution challenging but also fascinating, as it reveals the many factors that shape a galaxy's life story. When astronomers classify stars, they group them into populations based on their age and chemical composition. Population 2 stars are older stars that contain relatively few heavy elements. These stars formed early in proto-galaxies, before many generations of stars had lived and died to enrich the gas with metals. Population 2 stars are found in the halos of galaxies, in globular clusters, and in the thick disks of spiral galaxies. They are the veterans of the galaxy, carrying information about conditions in the early universe. Because they formed when the gas was still mostly hydrogen and helium with only traces of heavier elements, population 2 stars have lower metal content than younger stars like our Sun. By studying population 2 stars in the Milky Way and other galaxies, astronomers can learn about the first few billion years of galaxy evolution and piece together the early history of star formation. When galaxies collide and merge, the outcome depends greatly on the relative sizes of the two galaxies involved. Minor mergers happen when a small galaxy merges with a much larger one, and these trigger mild starbursts. A starburst is a period of intense star formation, much higher than the galaxy's normal rate. In a minor merger, the smaller galaxy's gas gets compressed and disturbed as it falls into the larger galaxy, triggering new star formation, but the effect is relatively modest because the smaller galaxy does not carry much gas. Major mergers, on the other hand, occur when two galaxies of similar size collide. These produce intense starbursts because both galaxies contribute significant amounts of gas, and the collision is much more violent. The gas from both galaxies crashes together, creating shock waves that compress the gas dramatically. This compression causes huge clouds of gas to collapse and form stars all at once. During a major merger, a galaxy can form stars hundreds of times faster than normal, using up its gas reserves quickly. The difference between minor and major mergers shows how the scale of an interaction determines its impact on star formation. Among the many mysterious objects JWST has discovered are small red dots scattered across images of the early universe. Astronomers are still debating exactly what these little red dots represent. They may be dusty starbursts, which are galaxies forming stars at high rates but shrouded in dust that absorbs blue and ultraviolet light and re-emits it at longer, redder wavelengths. Alternatively, they might be galaxies containing actively feeding black holes that emit reddish light. Some of these red dots might even be a combination of both processes happening at once. The compact size and red color of these objects make them stand out, but determining their true nature requires detailed spectroscopic observations. Each possibility has different implications for our understanding of the early universe. If they are dusty starbursts, it means dust formed remarkably early. If they are black holes, it tells us about how quickly supermassive black holes could grow. The little red dots are one of the ongoing puzzles that JWST is helping astronomers solve. In galaxy clusters, where many galaxies crowd together in a relatively small volume of space, the gas between galaxies undergoes a process called virialization. Virialization is a term from physics that describes how a system reaches a stable state where gravitational energy and kinetic energy balance each other. In a cluster, this means the gas is heated to very high temperatures, often millions of degrees, by the gravitational energy released as matter falls into the cluster. The gas in a virialized cluster is so hot that it glows in X-rays. Early in a cluster's history, active galactic nuclei feedback can accelerate this heating process. Black holes at the centers of galaxies inject additional energy into the surrounding gas through jets and winds. This AGN feedback heats the intracluster gas even more, sometimes preventing it from cooling and forming new stars. The combination of virialization heating and AGN feedback creates a hot, diffuse gas environment in galaxy clusters that can profoundly affect the galaxies living there. One of the key questions in galaxy formation is how rotating disks acquire their spin in the first place. The answer involves something called tidal torques, which impart angular momentum to collapsing gas clouds. Tidal torques arise from the uneven gravitational pull exerted on a gas cloud by the surrounding matter distribution. Imagine a gas cloud sitting in space, and nearby there are clumps of dark matter pulling on it. The gravitational pull is not the same on all sides of the cloud because the dark matter clumps are distributed asymmetrically. This uneven pull twists the gas cloud, causing it to start rotating. As the cloud collapses, it spins faster due to conservation of angular momentum, just like an ice skater spinning faster when pulling in their arms. Tidal torques are the mechanism that turns a non-rotating or slowly rotating cloud into a rapidly spinning disk. Without tidal torques, galaxies would not spin, and we would not see the beautiful spiral structures that characterize disk galaxies. When two disk galaxies merge, the orientation of their spins relative to each other matters a great deal. Misaligned mergers, where the two disks are spinning in different directions or at steep angles to each other, disrupt disks and scramble the orderly motion of stars. The gravitational interactions in a misaligned merger shake up the stellar orbits so much that the resulting galaxy loses its disk structure and becomes more spheroidal. This is one way elliptical galaxies can form from spiral galaxies. On the other hand, aligned mergers, where the two disks are spinning in roughly the same direction and in the same plane, can preserve thin disks. In an aligned merger, the two disks can settle down together into a single, thicker disk without destroying the overall disk structure. The stars from both galaxies end up in orbits that are all rotating in the same direction, maintaining the flattened shape. This shows that not all mergers are equally destructive. The geometry of the collision determines whether the disk survives or gets destroyed. Many spiral galaxies, including our own Milky Way, have a feature called a bar. A bar is a straight or slightly curved structure of stars that stretches across the galaxy's center. Bars form when instabilities in the disk amplify what are called non-axisymmetric modes. In a perfectly smooth, symmetric disk, every point at a given radius from the center experiences the same gravitational pull. But real disks are not perfectly smooth. They have density variations that create asymmetries. Non-axisymmetric modes are patterns or waves in the disk that do not have perfect circular symmetry. When certain instabilities occur, these non-axisymmetric patterns can grow stronger over time. Stars respond to the pattern by moving in ways that reinforce it, creating a self-sustaining wave. This wave appears as a bar structure. The bar then affects the motion of gas and stars in the galaxy, funneling material toward the center and changing the disk's overall shape. Bars are a natural consequence of disk dynamics and appear in about 2/3 of spiral galaxies. Even without major mergers, galaxies can change significantly over time through a process called secular evolution. Secular evolution reshapes disks via internal processes like spiral arms and bars that develop naturally within the disk. Spiral arms are density waves that rotate through the disk, and as stars and gas move through these arms, they experience gravitational forces that can change their orbits slightly. Over billions of years, these small changes add up, redistributing mass within the disk and potentially building up bulges at the center. Bars also drive secular evolution by transporting angular momentum and funneling gas inward. The term secular means slow and gradual, happening over long timescales without dramatic events. Secular evolution is like the slow aging process of a galaxy, distinct from the sudden changes caused by mergers. Understanding secular evolution helps explain how galaxies continue to change even in relatively quiet phases of their lives. The environment a galaxy lives in has a profound effect on its evolution. In galaxy clusters, where many galaxies are packed together and moving at high speeds through hot intracluster gas, star formation can be quenched through a process called ram pressure stripping. Ram pressure is the pressure exerted on an object moving through a fluid, like the wind you feel when riding a bicycle. As a galaxy moves through the hot intracluster gas, the ram pressure pushes on the galaxy's own cold gas, which is the fuel for star formation. If the ram pressure is strong enough, it can strip the cold gas right out of the galaxy, leaving it without the material needed to form new stars. The gas gets pulled out behind the galaxy like the tail of a comet, forming what astronomers call a tail of stripped gas. Without cold gas, the galaxy's star formation gradually shuts down, and it fades to red as its blue stars age and die without being replaced. Ram pressure stripping is one of the main ways galaxy clusters quench star formation in their member galaxies. Another way that dense environments affect galaxies is through a process charmingly called harassment. Harassment occurs from high-speed encounters between galaxies that disrupt disks without actually merging. In a galaxy cluster, galaxies are moving very fast, often at speeds of thousands of kilometers per second. When two galaxies pass close to each other at these high speeds, they do not have time to merge, but their gravitational interaction still disturbs each other. These repeated high-speed flybys can heat up the disk, puffing it up and making it thicker. They can also strip away outer stars and gas. Over time, multiple harassment events can transform a thin disk galaxy into a thicker, more diffuse system. Harassment is especially effective in clusters where galaxy encounters are frequent. It is another mechanism that helps explain why galaxies in dense environments often look different from galaxies in isolation. Not all galaxies live in massive clusters or in complete isolation. Many galaxies reside in galaxy groups, which are intermediate in size between isolated galaxies and large clusters. Galaxy groups show intermediate quenching behavior. They quench star formation more than isolated galaxies but less than galaxies in massive clusters. This makes sense because groups have some of the environmental effects that quench star formation, such as tidal interactions and some hot gas, but these effects are weaker than in clusters. Groups might have a few galaxies interacting with each other, causing mergers and disturbances that can affect star formation. They might have some warm gas between galaxies, though not as hot or dense as the intracluster gas in massive clusters. The intermediate nature of groups makes them interesting laboratories for studying how environment affects galaxies. By comparing galaxies in isolation, groups, and clusters, astronomers can untangle which environmental factors are most important for controlling star formation and galaxy evolution. Galaxies that live far from clusters and groups, out in the quiet regions of space, are called field galaxies. These galaxies enjoy a very different evolutionary path compared to their counterparts in dense environments. Field galaxies evolve slower and can accrete fresh gas for much longer periods. Without the ram pressure stripping, harassment, and other environmental effects that plague cluster galaxies, field galaxies can hold onto their gas and continue pulling in new material from the intergalactic medium. This steady supply of fresh gas allows them to sustain star formation over billions of years rather than having it suddenly shut off. Field galaxies can grow gradually and peacefully, building up their stellar populations bit by bit. The Milky Way itself is a field galaxy, living in a relatively quiet neighborhood with only a few nearby companions. This peaceful environment has allowed our galaxy to maintain its beautiful spiral structure and continue forming stars at a moderate rate for billions of years. The contrast between field galaxies and cluster galaxies shows how profoundly environment shapes galactic destiny. When astronomers study the early universe, they use various techniques to identify young, star-forming galaxies at great distances. One important class of objects is Lyman break galaxies at redshifts around 6 to 8. These galaxies mark a peak period of star formation in cosmic history. The name Lyman break comes from a feature in their spectrum related to hydrogen absorption. Young, star-forming galaxies produce lots of ultraviolet light, but hydrogen gas absorbs light at wavelengths shorter than a specific point called the Lyman limit. This creates a sudden drop or break in the galaxy's brightness at ultraviolet wavelengths. Because of the expansion of the universe, this break gets shifted to longer wavelengths for distant galaxies, allowing astronomers to identify them in optical images. Lyman break galaxies were forming stars vigorously when the universe was less than 1 billion years old. They represent an important phase of galaxy evolution when many galaxies were building up their stellar mass rapidly. By studying Lyman break galaxies, astronomers learn about the conditions and processes that dominated star formation in the early universe. Another important population for understanding galaxy evolution is submillimeter galaxies. These objects trace dust-obscured starbursts that would be invisible in ordinary optical images. Submillimeter galaxies are forming stars at extraordinary rates, sometimes hundreds or even thousands of solar masses per year. All this star formation produces copious ultraviolet light, but the galaxies contain so much dust that the ultraviolet light gets absorbed before it can escape. The dust heats up and re-emits the energy at much longer wavelengths in the submillimeter part of the spectrum. This is why they are called submillimeter galaxies. To detect them, Astronomers need special telescopes sensitive to these long wavelengths, such as the Atacama Large Millimeter Array. Submillimeter galaxies are thought to represent a phase that many massive galaxies went through, a period of intense star formation hidden behind veils of dust. They are building stellar mass quickly and may be in the process of transforming into the massive elliptical galaxies we see in the present-day universe. Sometimes astronomers find objects in the nearby universe that seem to be cosmic fossils or analogues of distant galaxies. One fascinating example is green pea galaxies, which represent local analogues of compact high-redshift systems. Green pea galaxies got their name because they appear as small, round, greenish objects in images. The green color comes from strong emission lines in their spectra that happen to fall in the wavelength range that looks green to our eyes. These galaxies are small, compact, and forming stars at very high rates relative to their size. They have properties remarkably similar to galaxies that existed billions of years ago at high redshift. Because green pea galaxies are relatively nearby, astronomers can study them in much greater detail than distant early galaxies. By understanding how green pea galaxies work, scientists gain insights into how star formation proceeded in the early universe. Green peas serve as local laboratories where the physics of primordial star formation can be examined up close. The universe contains a surprising diversity of galaxy types, including some that are so faint they were only discovered recently. Ultra-diffuse galaxies are low-surface brightness systems that are spread out over large volumes. They contain relatively few stars compared to their size, making them appear ghostly and translucent. An ultra-diffuse galaxy might be as large as the Milky Way but contain only 1% as many stars. Because their starlight is spread so thinly, they are extremely difficult to detect and were missed in earlier surveys. Only with modern imaging techniques have astronomers found significant numbers of them. The existence of ultra-diffuse galaxies raises interesting questions. How did they form? Why do they have so few stars despite being so large? Are they failed galaxies that never managed to form many stars, or did they lose most of their stars somehow? Understanding ultra-diffuse galaxies helps complete our picture of the full range of galaxy types that exist. Astronomers have discovered several empirical relationships that connect different properties of galaxies. One of the most important for spiral galaxies is the Tully-Fisher relation, which correlates luminosity with rotation velocity. Luminosity measures how bright a galaxy is, which is related to how many stars it contains. Rotation velocity measures how fast the galaxy is spinning. The Tully-Fisher relation says that more luminous spiral galaxies rotate faster. This makes sense if you think about it. A galaxy with more stars also has more mass, both in stars and dark matter. More mass means stronger gravity, and stronger gravity means gas and stars orbit faster. The Tully-Fisher relation is remarkably tight, meaning it holds with little scatter for most spiral galaxies. This makes it useful as a distance indicator. If you measure how fast a spiral galaxy is rotating, you can use the Tully-Fisher relation to estimate its true luminosity. Then, by comparing the true luminosity to how bright it appears from Earth, you can calculate how far away it must be. For elliptical galaxies, a different relationship is important, called the fundamental plane. The fundamental plane links several properties of elliptical galaxies together in a three-dimensional relationship. These properties include the galaxy's size, the average speed of stars moving within it, and its surface brightness. Just as the Tully-Fisher relation shows that spiral galaxies are not random but follow a pattern, the fundamental plane demonstrates that elliptical galaxies also obey systematic relationships. The fundamental plane exists because elliptical galaxies are virialized systems where gravity and the random motions of stars balance each other. Galaxies that lie on the fundamental plane are in equilibrium, with their properties related in predictable ways. Like the Tully-Fisher relation, the fundamental plane can be used to estimate distances to elliptical galaxies, making it a valuable tool in cosmology. It also provides clues about how elliptical galaxies formed and evolved. When astronomers compare galaxies at different cosmic epochs, one striking trend emerges in the size-mass relation, which shows that early galaxies were more compact than present-day galaxies of the same mass. A galaxy in the early universe with the same stellar mass as a modern galaxy would be significantly smaller. This means stars were packed more densely together in early galaxies. Why were early galaxies so compact? Several factors may contribute. Early galaxies formed in regions where gas was dense and collapsed efficiently, creating small, concentrated stellar systems. Minor mergers over time can puff up galaxies, making them larger without adding much mass. Disk instabilities and interactions can also cause galaxies to expand. The fact that galaxies have grown in size over cosmic time, even while adding mass through continued star formation and mergers, tells us something important about the physical processes governing galaxy structure. Understanding why early galaxies were compact helps constrain models of how galaxies assemble and evolve. One of the most fundamental relationships discovered in recent galaxy studies is the star formation main sequence, which links star formation rate and stellar mass. When you plot the star formation rate versus the stellar mass for a large sample of galaxies, most galaxies fall along a relatively narrow band called the main sequence. Galaxies on the main sequence are forming stars in a steady, regular manner. More massive galaxies tend to form stars faster than less massive galaxies, but the relationship is fairly tight. Galaxies that fall above the main sequence are forming stars faster than typical and might be experiencing a starburst. Galaxies below the main sequence are forming stars more slowly and may be in the process of quenching. The existence of a star formation main sequence suggests that there is a self-regulating process that ties a galaxy's star formation rate to its mass. Gas supply, feedback processes, and the rate at which gas can cool and collapse all work together to keep most galaxies on the main sequence. Deviations from the main sequence indicate that something unusual is happening to push a galaxy off the typical evolutionary track. Modern computer simulations have become incredibly sophisticated in modeling the complex physics of galaxy formation. The illustrious TNG simulations are among the most advanced. One aspect these simulations must get right is primordial metal line cooling. In the early universe, gas was almost entirely hydrogen and helium, with only trace amounts of heavier elements or metals. As stars formed and exploded, they added metals to the gas. Even tiny amounts of metals dramatically change how gas cools because metal atoms can radiate energy much more efficiently than hydrogen or helium alone. Illustrious TNG models this primordial metal line cooling process, tracking how the first generations of stars enriched the gas and how that enrichment affected subsequent star formation. Getting the cooling physics right is essential because cooling determines whether gas can collapse to form stars. If the cooling is too efficient, too many stars form too quickly. If it is not efficient enough, star formation proceeds too slowly. By carefully modeling metal line cooling, illustrious TNG simulations can reproduce the observed properties of galaxies at different epochs, building confidence that the simulations capture the real physical processes at work. The computer simulations that model galaxy formation require solving incredibly complex equations describing how gas behaves under gravity, pressure, and other forces. One technique used in advanced simulations like illustrious TNG involves moving mesh codes that solve hydrodynamics on dynamic grids. To understand what this means, imagine dividing space into many small cells, like a three-dimensional checkerboard. In traditional simulations, these cells stay fixed in place. But in moving mesh codes, the cells themselves can move and reshape to follow the flow of gas. This is like having a net that deforms to match the shape of whatever you put in it. The advantage of a moving mesh is that it can adapt to the structure of the gas. Where gas is dense and interesting things are happening, the mesh can have many small cells providing high resolution. Where gas is sparse, the mesh can have larger cells, saving computational resources. Moving mesh codes provide an elegant way to track gas flows accurately while using computer power efficiently. They represent a major advance in simulation technology and are part of why modern simulations can reproduce galactic structures in such impressive detail. Not all approaches to understanding galaxy formation rely on running full hydrodynamic simulations. Another powerful technique uses semi-analytic models that track gas flows on merger trees. A merger tree is a diagram showing how dark matter halos merge and grow over time. Semi-analytic models start with these merger trees, which can be extracted from dark matter-only simulations that are much faster to run than full simulations. Then the models apply approximate mathematical recipes to follow what happens to the gas and stars within those halos. These recipes include prescriptions for how gas cools, how stars form, how feedback works, and so on. The advantage of semi-analytic models is that they are computationally cheap, allowing scientists to quickly explore different assumptions and parameters. They can run thousands of model variations to see which best matches observations. While they sacrifice some physical detail compared to full simulations, semi-analytic models are invaluable tools for exploring the parameter space of galaxy formation and for making predictions that can be tested against observations. With multiple simulation codes and modeling approaches available, it becomes important to compare them and understand where they agree and disagree. The NIFTY Cluster Comparison Project was designed to isolate physics differences between various simulation codes. NIFTY stands for Numerical Investigation of a Fundamental Test, and the project involved having different research groups simulate the same galaxy cluster using their different codes and techniques. By giving everyone the same initial conditions and the same basic physics to include, the comparison could reveal which differences in the results came from genuine physics uncertainties versus which came from numerical methods. The NIFTY comparison helped the community understand the strengths and limitations of different simulation approaches. It highlighted areas where different codes agreed well, giving confidence in those predictions, and areas where they disagreed, pointing to where more work is needed. Such comparison projects are essential for ensuring that conclusions drawn from simulations are robust and not just artifacts of a particular code. While dark matter is generally assumed to be cold, meaning its particles move slowly, and non-interacting, meaning dark matter particles pass through each other without colliding, alternative models exist. One such alternative is self-interacting dark matter, which creates cores in dwarf galaxy halos instead of the cuspy density profiles predicted by standard cold dark matter. In self-interacting dark matter models, dark matter particles can scatter off each other, though weakly. This scattering redistributes dark matter from the dense centers of halos to the outer regions, creating a flat core rather than a steep central cusp. Observations of dwarf galaxies have sometimes suggested they have cores rather than cusps, which has motivated interest in self-interacting dark matter. However, the observational evidence is still debated, and it is possible that baryonic processes like supernova feedback can also create cores. Self-interacting dark matter remains an active area of research, with scientists working to determine whether the data truly requires it or whether standard cold dark matter plus realistic galaxy physics can explain everything we see. Another alternative to standard cold dark matter is warm dark matter, where dark matter particles have higher velocities than in the cold dark matter scenario. Warm dark matter suppresses small-scale structure because the faster-moving particles smooth out density fluctuations on small scales. In a warm dark matter universe, the smallest dark matter halos never form because the particles are moving too fast to be captured by weak gravitational wells. This would mean fewer dwarf galaxies and less substructure within large galaxies. Some observations have hinted that there might be less small-scale structure than standard cold dark matter predicts, leading to interest in warm dark matter models. However, like self-interacting dark matter, warm dark matter faces challenges. Observations of the distribution of galaxies and of gravitational lensing effects generally support cold dark matter, and it remains the standard assumption. Still, keeping an open mind and testing alternatives is good scientific practice. To rigorously test different dark matter models, scientists have developed comparison projects like IEDAR-TNG, which tests cold dark matter versus warm dark matter and self-interacting dark matter. IEDAR stands for Artificial Intelligence for Dark Matter and Astrophysics, and TNG refers to its connection with the illustrious TNG simulations. The project runs simulations with the same astrophysical processes but different assumptions about dark matter. By comparing the resulting galaxies and their properties, researchers can identify observational signatures that would distinguish between the models.
More self-interacting dark matter models can have additional complexity because the strength of interactions might depend on the relative velocities of the dark matter particles. Velocity-dependent self-interacting dark matter affects dwarf galaxies strongly while having less impact on larger systems. If dark matter particles interact more strongly at low velocities, the scattering would be most important in dwarf galaxies where dark matter particles move slowly. In larger, more massive galaxies where dark matter particles move faster, the interactions would be weaker. This velocity dependence could potentially explain why dwarf galaxies seem to have cores while larger galaxies appear consistent with cuspy profiles. It provides a way to have self-interacting dark matter solve certain small-scale problems without conflicting with observations of larger galaxies. Testing velocity-dependent models requires detailed simulations and careful comparison with a wide range of observations spanning different mass scales. It exemplifies how sophisticated modern dark matter theories have become. Within simulations, star formation must be implemented through specific algorithms since the simulations cannot resolve individual stars. One common approach is that gas cells exceeding certain density thresholds enter what is called the star-forming regime. When a cell of gas becomes dense enough and cold enough, the simulation identifies it as capable of forming stars. The gas in that cell is then converted into stellar particles according to specific rules. The density threshold is typically set based on observations of molecular clouds in our own galaxy, where star formation actually occurs. By requiring gas to exceed this threshold, Simulations ensure that stars only form in the appropriate dense regions rather than throughout the entire galaxy. This approach is a simplification of the complex, turbulent process of real star formation, but it captures the essential feature that stars form from cold, dense gas. Getting this threshold right is important for producing galaxies with realistic stellar masses and star formation rates. When gas cools in a simulation or in the real universe, it often does not remain smooth and uniform. Instead, radiatively cooling clouds fragment into clumps. As gas radiates away its energy, different regions cool at slightly different rates due to small density variations. The cooler regions become denser because their pressure drops and surrounding gas compresses them. These denser regions cool even faster, creating a runaway effect. The result is that a large, cooling cloud breaks up into many smaller, denser clumps separated by lower density gas. This fragmentation process is important for star formation because it creates the range of cloud masses and densities observed in star-forming regions. Simulations that properly capture radiative cooling naturally reproduce this clumpy structure. The clumps can then collapse further to form individual stars or clusters of stars, depending on their mass and the local conditions. One of the subtle but important aspects of gas dynamics in galaxy formation involves something called dissipative processes, which enable cooling below the gene's mass. The gene's mass is a critical threshold in astrophysics. It represents the minimum mass a gas cloud must have to collapse under its own gravity despite internal pressure trying to resist collapse. You might think that gas clouds smaller than the gene's mass could never collapse and form stars. However, dissipative processes change this picture. Dissipation means processes that remove energy from the system, and in gas clouds, radiative cooling is the main dissipative process. As a cloud radiates energy away, it cools and its pressure drops. This lowers the gene's mass, meaning that smaller clouds can now collapse. Through continued cooling, gas can fragment into clumps smaller than the original gene's mass and still collapse to form stars. This dissipative cooling is crucial for understanding how a single large cloud can fragment into many smaller pieces that each form stars. It explains why we see star clusters with many individual stars rather than just single massive objects. The interplay between gravity, pressure, and cooling determines the detailed structure of star-forming regions and ultimately the mass distribution of stars, connecting the physics of galaxy formation down to the scale of individual stellar birth.